Ses deneme, ses. Ses deneme. I share the screenshot of our piece. Okay, everything's done. Hi everyone, welcome back again. This week we will talk about some fundamentals of this our artificial intelligence course. This week, today, we are finally going to dive into the core ideas of artificial intelligence, how it actually works behind the scenes. Until now, we have talked about what AI is, where it's used, and how it's shaping our world. But now it's time to look under the hood and to understand the structures that might make AI intelligent. And so today we will start exploring one of the most important parts of AI, artificial neural networks. These networks are basically the building blocks of modern AI systems, especially the ones used in deep learning. Let's start simple. The idea of neural network comes from human brain. Our brain is made up of billions of neurons that send electrical signals to each other. Each neuron receives input, processes it, and sends output to the next neuron. AI researchers thought, what if we could build something similar for machines? That's how artificial neurons were born. It is mainly inspired by the way human brain works. Sorry, just a second. I couldn't see the screen because of the sunlight. Sorry about it. Okay, let's continue. What I said just now, each the artificial neurons is just like the human biological neurons, and each typical neuron or perceptron, I mean, in our computer science, we call it perceptron, takes some inputs like numbers. These inputs are the symbols, the info about what we are analyzing. And we take some inputs, multiplies them by weights, which show how important each input is, and adds them up, and then passes them through something called an activation function. Let me change the screen. Activation function, and the activation function decides whether that neuron should be activated or not. Kind of like saying, is this signal strong enough to react to? I mean, this function determines under what conditions the neuron becomes active. You can think about it as in your normal life. You don't react every actions around you. People do something to you, but you choose not to act to that actions. You don't react them, and it is the same version in computer science. We don't react every action. We choose, and activation function tells us what to choose. And the question is this signal strong enough to react to? If it's not, we keep going. Let me give you an example. Imagine you are building a small AI that recognize handwritten digits. Handwritten digits, just like here. You can check it out, handwritten digits. The numbers 0 to 9. At first, the network has no idea what a tree looks like, but after showing it thousands of examples, it starts adjusting its internal weights until it can recognize a new tree that it is never seen before. This is how a neural network learns, by adjusting itself little by little each time it makes a mistake. And now a single neuron can't do much, just like one brain cell can't think on its own. But when we connect thousands, even millions of them together in different layers, that when things start to get powerful. Look at this example. There are some digits written on the screen, but it is actually not enough to learn, because you need to see the different types of these digits, maybe million different types, because learning comes with seeing different outputs. If you don't have enough different version of these digits, then you cannot learn well. And when we look at the 7, there are really not the same pattern. All of them is actually have different patterns, and by seeing these differences between digits, you learn more and more. And it's important at the first step to gather millions of different data to learn. And let me change the page. And as we see on the screen, there are input layer, inputs. This is the basic neural network, has these layers. First one is input layer, where data first comes in, like the pixels of an image or sound waves of a voice. Then after that, hidden layers come, where the actual learning happens in hidden layers. Each layer transforms the data into something more meaningful. And the output layer, where final result comes out. For example, it tells you this is a cat, or this is a dog, or this is a table. When a network has many hidden layers, we call it deep learning. That's why systems like ChatGPT or the other DeepSeek, other types of artificial intelligence tools, image recognition models, or voice assistants are often called deep learning models, because they use many layers and processing them to learn complex patterns. There are also different types of, you can analyze this picture and ask Google about what is scores. Scores means grades. What is hidden units? How many hidden units do I have to have? What's the optimal number for these activation functions? Because it's up to your model. It's up to your strategy. If you want to have shallow layer based artificial network, then you need to have these layers in small numbers. But if you have to analyze them and looking deeper into the network, you need to have many layers to analyze all these changes. And this is what I just talked about. And there are also some different types of neural networks depending on what kind of data we are dealing with. For example, you see three different networks here. First one is feed-forward neural network, FNN. Feed-forward networks are the simplest kind. The data moves straight from input to output, flows only in one direction, often used for simple prediction and classification tasks. After that, convolutional neural network comes, or CNNs, are used for image processing. They are great at recognizing shapes, colors, and edges. So when your phone recognizes a face in your photo, that's a CNN network, commonly used for image processing. If you have no idea about what is convolution, you can check it out on Wikipedia. Let me show you. Convolution. You can read all these texts, but mainly I can tell you in mathematics, convolution is a mathematical operation, just like multiplying, just like adding, just like subtracting. It's the beyond four of these fundamental operations. It's, we can say, fifth operation of mathematical in mathematics. Convolution is a mathematical operation on two functions, f and g, that produces a third function, f convolution with g, as we can see here, as the integral of the product of two functions after one is reflected about the y-axis and shifted. Just we can check it from here. F comes on top of G, and the signal changes, and it goes after that F. And we analyze these changes, and after that, the last shape of signal is important for us. The term convolution refers to the both the resulting function and to the process of computing it. The integral is evaluated for all values of shift, producing the convolution function. The choice of which function is reflected and shifted before the integral doesn't change the integral result. It's an important, something different we can see and analyze from concavity. Graphically, it expresses how the shape of one function is modified by the other. It is actually not the topic of artificial intelligence. It's related to signal processing. We have this signal processing course in our computer engineering department, but for you guys, you don't need to analyze what's convolution, but I'm just telling you to have some ideas in your mind when we say convolution. It's really generally used in probability, statistics, and all these engineering part, physics, computer vision, all these areas. And it's really well-known something in statistics. There are, as you see, mathematical formulations to have these results, but in basic, I can tell you when two different signals comes together, you can check it out from here. This signal comes and change the other signal. Then on the top of the next signal comes, look at and the final result, final signal F, convolution G, comes as an output. It's about, you can see the red pulse, and after the red pulse comes to on the blue pulse, and the final result in black line. You can see this triangle. It's used in many areas, as I told you. Look at this discrete 2D convolution. You multiply all these 9 digits and it becomes 1 digit. Just, you can see 0 minus 9 and the other things. This is really good exercise to learn what it is. This framework comes on top of every digit, and by doing this you will have just one digit after these analyses, and it means that's the main operation of 2D convolution animation. As I told you, it's really related to computer engineering, but if you want to look deeper and analyze, you can check this page out. Okay. Convolution. Now we keep going from the presentation. And after that, recurrent neural networks, RNN, comes. They are used for sequences like speech, text, or time series data. They can remember information over time, which is why they are used in things like Siri, Google Assistant, and music prediction apps. It's commonly related to sequential data, as I told you, and they can remember previous information. That's important. For instance, a CNN might detect a tumor in an MRI X-ray image, while an RNN could analyze a patient's heartbeat, because as I told you before, it flows only in one direction. RNN only handles with sequential data, and ECG or EEG signals are sequential data. So RNN model analyzes these signals over time to detect abnormalities. Both are neural network, they just process information differently. This is the convolution architecture, convolution neural network architecture. We have some operations like pooling operation, kernel padding. After that, again, the second level pooling. After that, you combine all these neurons, perceptrons, and then these classes tells you this digit belongs to number 2, second class. So it is not easy to analyze what the digit is. It can be 0 to 9. There are 10 different classes, and after these analyses you can tell that this image belongs to number 2. But as I told you, these CNNs can have many layers inside it, and if you have many layers, deeper levels, then your architecture becomes deep learning process. It's really popular these days. Let's talk about now for activation functions, because they are really a key part of how the neural network make decisions. Imagine if a neuron reacted to every input equally, that wouldn't be very smart. We need a way to decide when a neuron should activate and when it shouldn't. There must be change in weights. If you say the weights are equal, then you don't learn anything, because if they are equal, you don't react. If you are clever, if your system is clever, then you are supposed to react to the actions around you. And these functions, activation functions, determine whether a neuron should fire or remain inactive. If you are inactive, you are not too clever, but if you fire something, then it means you react to outputs around you, and it's good thing. It's a good sign. Some popular activation functions are, first one is sigmoid, which squashes outputs between 0 and 1. All the digits turns into a range between 0 and 1, kind of like saying yes or no. It's a really common thing in probability-based models, sigmoid function. And after that, rectified linear unit. Rectified linear unit comes, which ignores negative values and passes positive ones. This one helps deep networks learn faster and is used almost everywhere today. Sets negative values to 0 and keeps positive. It's the main thing. And it's the most popular choice in deep networks. And also we have softmax, which turns outputs into probabilities. For example, it might say there is an 80% chance this is a cat, 90% chance it's a dog. It's related to probability distributions and useful for multi-class classifications. And let's look at different learning dynamics. Learning happens through a process called backpropagation. A neural network continuously adjusts its weights by backpropagation until it makes accurate predictions. Backpropagation, which is just a fancy way of saying the network learns from its mistakes. Here is how it works. The model makes a prediction. We compare it to the correct answer. It calculates how wrong it was. Then it goes back and adjusts all the weights a little bit to be more accurate next time. After doing this thousands of times, the model becomes smarter and smarter. It's important the repeating number of this process. Maybe thousands times, maybe million times. The network learns from its mistakes and improves its accuracy. You can think of it like a student practicing math problems. The first few times they get along wrong, but each time they see where the mistake was, fix it and improve. That's exactly what neural networks do. They just learn from data instead of textbooks. Let's look at some the architecture about this learning dynamics. There is an update step, and after that, feed forward calculation comes, observation output and model output. If the model output is the same with the observations, that's a good thing because your model predicts good. If there is a difference and big difference between these two outputs, then you need to, and if the error level is under the tolerance, you need to go back and update your weights, And after updating it, your difference between observation and model results becomes less. And it means becoming less, it means you become clever. You get clever, but smarter. But if the difference between observation and the model outputs results, if it's getting bigger, then it means you don't learn anything from this mathematical formulation. There is something wrong in your architecture. You need to change it. You need to find another maybe model. Maybe you are supposed to use different approach. Like RNN is not enough for you. You can change it to CNN, or maybe CNN is not enough for you. You can change it to DNN, deep neural network. And all these strategies gives you the smarter results. When you get your smarter result, you choose your approach. And until the choosing, you are doing this procedure again and again, this backpropagation procedure, because you need to learn something and you need to check your error. If your error is under the tolerance, it's maybe good, but if it's bigger than the tolerance, you need to change something in your model. Model your approach, everything maybe from the scratch. You need to find a new way or use a new model. And by doing this, you are becoming clever, smarter. Let's look at, and this is a different picture. Tells that there are weights, there are inputs, there are mathematical formulation, and after that, this result goes to activation function, and after activation function, there are a different result, and you look at this result, and you need to calculate your cost function. Cost function means the difference between observation and the model outputs. And if the cost is high, so you need to backpropagate and weight updates them. After weight updating, you again send your input function to activation function, and you get different result. And after that, you calculate your cost function. If it's higher than you expect, then you do backpropagation again and again and again, thousands times, until you get the result that you are looking for. And if it's good for you, if it's fit for you, then you will pass it to output result. Let's look at some real world examples so you can picture it better. You can get big picture in your mind better. When Google Photos recognizes your face, or Instagram tags your friend automatically, that's a deep neural network, specifically a CNN, especially CNN. Or when Alexa or Siri understand your voice and response, it's using an RNN trained on speech data because, as I mentioned before, RNN is related to sequential data, and your voice is a sequential data. Speech data is sequential. So you need to use RNN. Also, when self-driving cars detect people, signs, or obstacles, that's also AI powered by neural networks combining vision and decision making. They use multi-layered deep networks to detect objects around you and make driving decisions. Also in healthcare, AI systems analyze X-rays and MRIs using CNNs to find tumors that human eyes might miss, because it's normal to miss your human eyes, not powerful that much as computers do. So to summarize what we learned today, neural networks are the backbone of modern AI. They're inspired by the human brain and built from connected layers of artificial neurons. Each layer helps the system learn a little more, transforming raw data into meaningful patterns. With the help of activation functions and backpropagation learning process, these models can learn from examples from big data sets, correct their mistakes, and make predictions about it, about new data. Maybe it's not seen before. Thanks to this structure, AI systems today can see, they can hear, they can understand, and also they can decide. Not perfectly, but impressively close to how humans do. Next time, next section, we'll go one step further and let's look at how these models actually learn, the learning process of AI models, how data flows through them, how we train them, how and what problems can appear, like overfitting or bias. But for now, for this section, I just want to remember one thing. Neural networks are not magic. They're just layers of math that learned how to learn. They just learned how to learn in maybe the last 10 years. And okay, let's pass to the second part of our course, the learning process of AI. Learning process, there are 4 different sections in this section. There are subsections. The understanding data and feature comes first. After that, training model and model testing and evaluation. And then common challenges in learning. In this part, we are taking the next big step. We are going to talk about how these models actually learn. So we are moving from structure to process. We will explore how the data flows through a model, how it learns from mistakes, and how we measure if it's doing a good job. First, understanding data and features. Let's start with something simple but incredibly important: data. Every AI system, no matter how advanced it looks, is only as smart as the data we feed it. This is important. AI systems are only as smart as the data we feed it. If the data is good, diverse, and well organized, the model learns useful patterns. But if it's messy, biased, or incomplete, the model gets confused. So, the quality of data directly determines how well a model performs. Think about it this way. Imagine you are teaching a child to recognize animals. But if you only show them pictures of brown dogs and never any white ones, they will think dog always means brown. That's exactly what happens when our training data is unbalanced and limited. The model learns the wrong lessons. Learning comes first with the clean data. We usually divide the data into three groups, three different groups. Look now, you can check that on the picture. Given data, all the data is you can see in with green lines, and we split it out to three different datas. Training set, which teaches the model. Training set, the portion of data used for learning and adjusting the model's parameters. After that, validation data comes, which helps us check how well the model is learning while training. How well the model is learning while training validation, used to test model performance during training and tune hyperparameters. Hyperparameters are changing parameters to decide and choose your strategy. And the test data, which is like the final exam. Data the model has never seen before. Test data. Completely separate data. Not from here, completely separate. And used to evaluate how well does the model performs on unseen examples that has never seen before. Okay, when we talk about features are inside this data. There are some features. Feature means we mean the measurable parts of the data. Measurable parts. Feature is an attribute or measurable property of data. If we are predicting house prices, for example, the features might be the number of rooms, the size of house, its location, and how old the building is. Maybe square meter digits, maybe again another digit about related to number of rooms, or how much square meter does it have, these rooms, maybe location, again, it's a numerical thing, or the age of building, again, the numerical data tells about the quality of the house. The model doesn't see a house. It sees numbers representing these characteristics. You need to capture these characteristic numbers. AI models learn the relationships between these features to make predictions. Before we can train, through the data needs cleaning. We often have to deal with missing values, scale differences, because it requires normalization generally in data processing. step, and also words instead of numbers. We choose numbers. Numbers are the data that have small memory need in your computer. So numbers are choosable. We pre-process the data, we normalize values, we convert categories to numbers, and sometimes even balance the data set so one class doesn't dominate all the data set. We need to have different kinds, different classes. Raw data, as it's written on the screen, is often noisy, incomplete, or unbalanced, so it must be cleaned and transformed before training. As I told you before, handling some missing values, normalization and scaling, adjusting value ranges. It's usually 0 from 100, converting categorical data into numerical form. We don't say male, we say 0. It represents male class. And also we don't say female, we say 1. It represents female class. And shuffling and balancing data sets, because one class shouldn't dominate whole data set. This stage is like giving the model clean, labeled flashcards before an exam. This was all about understanding data, analyzing data, logging data, and capturing the high quality features from those data. And after that comes next step, training the model. Now comes the fun part, training. Training is basically teaching the model through trial and error. Again, training process is how a model learns from data by adjusting its internal parameters to minimize error. This process revolves around two main ideas: error calculation and optimization. Here is what happens step by step. First step, the model looks at the input data and makes a prediction. Then the difference between the predicted data and the actual value is calculated. We compare the prediction to the correct answer and calculate how wrong it is. That's called the loss. Okay, the third step is then in the third step, we send that error backward through the network in a process called backpropagation. The error is propagated backward through our network. And in fourth step, the model updates its internal settings called weights to do a little better next time, because we come close little to the output, and if we do it in big steps, that's not good. We need to approach little, and after thousands of operations, we get the best optimum result. This cycle repeats thousands, sometimes millions of times, and each full pass through the entire data set is called an epoch. Epoch is another important term in our neural networks in our systems. Each full pass, as I told you before, each full pass through the entire system is called an. The model slowly improves, much like a student practicing math problems every day and getting faster and more accurate with time. The goal is to make the model gradually more accurate. To measure how wrong the model is, we use loss function. For example, when predicting numbers, we might use mean squared error, basically the average of all the squared mistakes. For classification tasks, like recognizing cats versus dogs, we use cross entropy loss, which measures how far the model is predicted probabilities are from the truth. Then we need an optimization algorithms. An algorithm that helps the model adjust its weights efficiently. These algorithms adjust the model's weights to minimize loss. The final reach is exactly number 0. We don't want to have any loss in our model, but it can't be. It's a utopia. You cannot choose or separate all the classes in a good way, in an optimal way. Of course, in your life you will have some losses, but the final reach is minimize your loss. You cannot say I will not have any loss in my life, in my model. You will have it, but minimizing is the final reach for our strategy. And more advanced optimizers, the simplest optimizer is gradient descent, which is like rolling down a hill, trying to reach the lowest point, the minimum error. More advanced optimizers like ADAM or RMSProp help the model move faster and avoid getting stuck halfway down the hill. These are different approaches in optimization strategies, but you start from the basic approaches, then you can change the methods, maybe up to your output results. First, you check your output results, and maybe if you need, you change your strategy, or you can keep going in your strategy. You can follow your last strategy if it's successful, but changing your path is not is a good thing actually in A&M, because you are trying to get your maximum, your optimum model approach in your model. So you need to you cannot have it in your first try. You need to try and change and getting smarter day by day in your model, and final destination is the optimum one, reaching the optimum one, and you are keep trying until reach there. One of the trickiest parts is the learning rate. It controls how big each adjustment step is. If the learning rate is too high, change the page. If the learning rate is too high, The model bounces around wildly and never settles. Again, I'm saying it controls how much the model updates its weights each time, the learning rate. If it's too high, model becomes unstable. If it's too low, it learns very slowly. You can learn fast in a faster way, but you become unstable in your decisions. If you do it too low, then you learn very slow. Maybe in 100 years you will learn. You will be clever, smart, but after 100 years, and it's not good. So you need to find an optimum learning rate in your model. Not too low, not too fast. It's low, it crawls so slowly that training takes forever. Finding that sweet spot is a bit like tuning an instrument. It takes some trial and error. And batch and epoch concepts tells you how good you are. Batch is a small subset of training data processed before updating the weights. And epoch is one full pass through the entire training system. You use these terms in your model to become better and better. These first two steps was understanding the features and training the model. And after that, third section, the model testing and evaluation, we will continue next week, because in model testing, there are some another terms like accuracy, precision, F1 score, and there are also many challenges, common challenges like overfitting, underfitting, data bias, and model drift, etc. It's going then. We will wrap up this learning process of models. But for today, we learned two different sections. First one was artificial neural networks and layered architectures. We learned the basic logic behind the artificial neural network. We learned layered architecture, what it means. We learned if we have many of those layers, then it means deep learning approach. And after that, activation functions comes to determine to be active or not. And also learning dynamics, I try to show you. And also, lastly, the real world examples gives you some idea in your mind to understand these approaches. CNN models related to convolution operations, RNN models related to sequential signals. Also, I told you about some common activation functions. And for this week, you can analyze these pictures here, shown in here. The hidden layer, the output layer, input layer. You can search all these layers on the internet or neurons. If we have another picture of neuron, you can check it out on the internet. Maybe you can check the differences between these pictures. Also, I try to show you learning dynamics, where the activation function stands in your model, or where the backpropagation stands in your model. Weight update comes after checking the cost function. These are all AI related terms, and you need to learn. Of course, in your exam, I will ask about these terms, and you need to give some sentences about these terms. And also in the second section, we look deeper into the learning process of AI models, the understanding data, and there are features in data. And you need to find these features. You need to utilize of these features. These are important things to capture the suitable and optimal features from the data. And it's really important, the quality of data, the patterns, it should be many patterns within data. If you have less patterns or just a few patterns, that's not good. You need to, if you want to learn, you need to see many types, different types of your data. And every AI model begins with analyzing this data. And we separate this data set into different sets, training set, validation test set. And after that, we capture features, as I told you, number of room is a feature of house price, and also size of the house is another feature of house price. And after that, we pre-process the data, we normalize, we converting categorical data into numerical form, 0 or 1. And then training process comes, and in the training model, I can ask you the error calculation is in data processing or training the model. Of course, error calculation is in training model. Also, optimization is in training set or validation set. I can ask you about, or test set. These are the questions to understand better what AI means. Also, in training model step, there's backpropagation. Also, I can ask you what we do in backpropagation, loss functions, the way it stands in backpropagation or before backpropagation. Also, what is, I can ask you, what is gradient descent? Gradient descent is an optimization algorithm. You need to know this, or tell me about learning rate. I can ask you, learning rate means it controls how much the model updates its weights. That's the best sentence to tell what the learning rate is. And as I told you just before, we will continue next week with model testing and evaluation. We are trying to get architecture of the AI, the components, main components of AI. We start this week to analyze the components. Also, in the next weeks, we will keep looking at this deeper, and also we will talk about how we use AI in different sectors, in different areas, because also we need to also give you a perspective about how to use AI in your professions. For this week, it's done. Thank you for everyone watching this video, and see you guys in next week. Have a great week.